In this video, we will be going over the Wheatstone bridge circuit again, this time with Thevenin's equivalent circuit. This simplifies this circuit down into a single voltage source, a single series resistor, and an open circuit. This is a much easier method to calculate the current I5 than the previous video, which I have linked down below. With this method, we choose 2 points on the circuit, which are these 2 points, and then we can simplify it out to find the voltage source and the resistor. Because we want to find the current I5, the best points to use are here and here. The first thing to do is remove R5 from the circuit, as it is going to be the open part of the circuit. I've moved R5 over to the right. Now we should label each of the 2 voltage points. We can label this side point A and this side point B. What we want to do first is find the equivalent resistance of Thevenin's equivalent circuit. To do that, we need to find the equivalent resistance from point A to point B. In order to do this, we need to short out this voltage supply. Now that the voltage supply is shorted, we can look at the circuit and try and understand what is actually inside the circuit. The possible paths for current to flow from A to B are up or down through either of these resistors, and then once they're out here or here, which we can see is electrically the same point, it can then move through R2 or through R4. And then to B. This can be rewritten as 2 sets of parallel resistors in series, like this. This is because when current comes from A, it can move in either to R1 or R3, and then once it comes out, it can then go to either R2 or R4. Now we can see that calculating the overall resistance from A to B is not particularly difficult. We have one set of parallel resistors in series with another set of parallel resistors. The first set of parallel resistors will have equivalent resistance of 1 over R1 plus 1 over R3. And the second set of resistors will have equivalent resistance of 1 over R2 plus 1 over R4. We can simply add these together to get the total equivalent resistance, which will be 1 over R1 plus 1 over R3 plus 1 over R2 plus 1 over R4. This is our Thevenin equivalent resistor. Next, we need to find the voltage difference between A and B in this circuit with this voltage source, and then create a new voltage source in the Thevenin equivalent circuit that would give the same voltage difference between A and B. Currently, in this circuit, the voltage at A will be the voltage taken up by R3, and the voltage at B will be the voltage taken up by R4. So A can be represented as R3 over R1 plus R3 times the voltage source, and B can be represented as R4 over R2 plus R4 times the voltage source. So if we wanted to find the difference between A and B, we would have A minus B is the voltage source times R3 over R1 plus R3 minus R4 over R2 plus R4. This is the voltage difference between A and B, also known as the voltage across the open circuit. Now that we have the voltage across the open circuit, and we have the equivalent resistance, we can make our Thevenin circuit with a voltage source, a resistor, and the open circuit with VO and R. As the open circuit has infinitely large resistance, this open voltage will entirely be taken up through here, and there will be no voltage lost over this resistor, so this will still be taking this VO, which is the same as A to B here. Now that we have our Thevenin equivalent circuit, we want to bring back our R5 resistor, and we want to put it in the circuit. In here. Now what we have is we have just a normal simple circuit with two resistors. We have the voltage over it, and we have the individual resistances. So the current going through R5 will simply be I equals V over R total, which is just I equals voltage open over R plus R5. Now let's do this with an example. Here is an example with some actual numbers. R1 is 12 ohms, R2 is 7, R3 is 26, R4 is 4, R5 is 17 ohms, and the voltage source is 12 volts. I've already created the diagram where I shorted the voltage source and drew the resistors from A to B in order to calculate the equivalent resistance, which is going to be, this part is 1 over 12 plus 1 over 26 plus this part, which is 1 over 7 plus 1 over 4. The equivalent resistance for this circuit is 10.76 ohms. And I'm keeping this full value in my calculator in order to make sure we don't have any rounding errors. Now we want to find the equivalent voltage source. So we can find the voltage at A, which is going to be the voltage over this resistor. Voltage at A is 12 volts times 26 over 12 plus 26, which is 8.211 volts. Again, still in my calculator. Then we find the voltage at B, which is 12 volts times 4 over 4 plus 7, which is 4.364 volts. I'm keeping that in my calculator. Then we have VA, we have VB. We can find the difference, VA minus VB, which is 8.211 minus 4.364, which is 3.847 volts to 4 significant figures. Now we have our resistance, we have our voltage. We can create our equivalent circuit. We have a voltage source with 3.847 volts. We have a resistor with 10.76 ohms, and we have our open circuit. Now what we can do is we can bring down the 17 ohm resistor, R5, from here, and we can put it back in the circuit between A and B. So here we'll have the 17 ohm resistor. And now we have a full circuit. What we can do to calculate current, which is just voltage over R total, is 3.847 over 10.76 plus 17, and I, passing through this resistor R5, is 0.1386 amps to 4 significant figures. Because we have a positive number, that means the current is going from A to B. If we had a negative number, it would be coming from B to A, but that's not the case. I5 here is 0.1386 amps.